Good afternoon, everyone, and thank you again for attending this webinar workshop on seismic hazard assessment and rapid visual screening of existing heritage buildings. And I would like to acknowledge the presence of our research collaborators from University of the Philippines, Visayas, my colleagues at De La Salle University, and collaborators from the Department of Civil Engineering of Central Philippine University, University College of London, and of course our guest from LGU, Iloilo City. So my topic would focus on detailed structural evaluation, the use of semi-destructive and non-destructive testing. So my presentation outline for today, first I would like to discuss an overview of the tiered process in conducting a seismic evaluation of existing buildings, and how can we utilize the information that we obtain from the rapid visual screening for a detailed evaluation. And then how can we move from the results of the rapid visual screening to a more detailed analysis, and what are the tests that are required or necessary for us to conduct detailed assessment. Then I would like to tackle a topic about benchmarking techniques and why is it important. And I will end my presentation by providing an overview of conducting a detailed structural evaluation. So please allow me to start. First, on the evaluation process, or the use of what we call the tiered approach in conducting seismic evaluation. Now, the tiered approach in conducting an evaluation on existing buildings can be generally classified into 3 tiers. But we understand that before we move to this tiered approach, we need to conduct what we call the rapid visual screening, which was discussed and explained to you today. Now, the rapid visual screening really is a tool that would help us classify the risks of existing buildings, which would then allow us to create a prioritization index, which would help us pinpoint the buildings which need urgent attention. In a overall sense, if we have a building stock that we want to assess, then the best way forward is first to do the RBS, then conducting a detailed assessment for all the buildings. In that way, we can just focus on buildings that are, I would say, that are more at risk in terms of the selected hazard. Okay. Now, following the RVS results, after we were able to classify these structures according to their risks, then we continue, okay, by identifying the buildings that are at risk to actually further assess them. Okay, further assess them to focus on identifying what we call the potential structural deficiencies. And in Tier 1 assessment, we have what we call a checklist, which would allow us to determine several structural and non-structural deficiencies in the structure that are important in ensuring the structural integrity of a building. This includes some quick checks as provided in ASCE 41. And from these quick checks, it allows us to determine the severity of the potential deficiency, which would then trigger the necessary intervention. And moving forward, if we want to actually move forward to doing some retrofit, then we need to do what we call a higher level of analysis that would include Tier 2 analysis. And in Tier 2 analysis, as as now defined in ASCE 41-13 and 17, is more on a deficiency-based type of analysis, meaning we will only focus on evaluating defects and deficiencies identified in the Tier 1 assessment without looking on the overall global performance of the building. Okay, so that is why it is focused on solving the structural deficiencies identified in the Tier 1 analysis. However, if we want to go further and somehow increase the level of confidence we have in the way we analyze an existing building, then we can conduct what we call a Tier 3 assessment. And the Tier 3 assessment is more systematic in a way that it's not just focused on the elements that were considered deficient based on a Tier 1 analysis, but it models the behavior of all the structural elements and utilizes state-of-the-art modeling techniques such as the use of nonlinear methods in order to determine the defects or in order to accurately determine which members needed retrofitting or strengthening. And that is the purpose of a Tier 3 analysis. Now, of course, the higher the tier level, the more sophisticated tools are needed in order to achieve a certain task. But in essence, also, the higher the level of assessment, it is possible that we can minimize the needed or required retrofit as a result of the type of assessment that we use. Then, how do we move forward from this tiered approach? Like, from the rapid visual screening results that we obtain, how can we use this information to proceed with a detailed assessment? Let's say we have now the RVS data. How can we use this RVS data in order for us to conduct a detailed assessment? If we look at the information that are provided in our RVS results, this would include the following. We have what we call the construction year, the material type, the structural framing system are also noted in this RVS form, the number of stories and building height, hazard information, what we call the seismic parameters, the building condition, and of course, for the RVS that was conducted for Iloilo, the presence of damage, defects, and deterioration are noted. And in some cases, we were able to note the typical structural member sizes. Now, the question is, from this data that we have, why is it important for us to determine the construction year? Well, historical information would suggest that the strength of concrete material somehow varies at a certain period of time since it was invented in United Kingdom. So here we can see in this slide a table which provide a time frame, okay, and the corresponding compressive strength of concrete within these durations. Okay, so for example, during the year 1900 to 1919, most of the beams were constructed with a compressive strength of concrete around 13.8 megapascal, while it was just way back in 1950 when really buildings have started using 21 megapascal compressive strength of concrete. So with this information, it already gives us an idea. So what could be the possible compressive strength of concrete used in a given structure? So if we have that construction year, we can somehow get that idea how much compressive strength can we expect from this given structure. Similarly, we also have what we call the steel material properties. And the reinforcing steel from the development of this type of materials used for reinforced concrete, like for example, from duration 1911 to 1959, that was the time grade 33 was introduced. And 1959 to 1966, that was the only time where grade 60 reinforcing steel was introduced in the market. And this is actually a US data. So more so, you can expect that this type of materials really reached the Philippines at a later year as compared to the years that are provided here in the slide. So, for example, if my building was constructed in 1911, then I should not expect that I would have a reinforcing steel having a material strength of around 60 KSI, or what we call the 420 megapascal strength. So that's how the information about the construction year is important, because we can always correlate this year of construction with the strength of materials that was used for constructing these buildings. Another information that we can get from the RBS is what we call the hazard parameters. For example, we can get information about the location, the coordinates of the building under consideration, and from that given location, we can use the app that was introduced earlier, which is the fault finder, and we can determine how far is our building from the nearest known active fault. And from that information, we can then determine the necessary seismic parameters that we can use for detailed assessment. Similarly, for wind, given the location of our building, then we can also pinpoint the wind speed that we should use in the assessment of a given structure. So that is how information like the coordinates obtained from the RBS are important. In terms of building function, this information then would allow us to somehow estimate the gravity loads that we should use in the assessment. So for example, based on the building use, we can estimate the superimposed dead load that we should use in the structural analysis, as well as the intensity of live load. So for example, if it is a commercial building now, probably a grocery or supermarket, then we can say that there are some storage area in those structures, so we will use a storage classification in terms of the occupancy, okay? And we will use that amount of live load intensity to assess our structure. And then it would also help us to classify the importance category. So for example, if the existing building probably is now used as a clinic or a makeshift hospital, then we can then classify it, oh, this is now an important facility, and therefore we should also assess it based on a higher level of importance. Then another information that we can get from the RBS is the information about the existing condition of the structure. So the condition of the building itself, as can be noted from the RBS result, like if there are cracks, if there are spalling, if there are corrosion or any form of displacement or deflection, then we can get those also from the RBS result, and from there we can able to determine the necessary step or the necessary tests that we should perform when we do a detailed assessment. So it also allows us to know if we need to do some immediate action in order to ensure the structural integrity of the building. So for example, if we saw some cracks, okay, if we saw some cracks in an existing structure, although we know that um, if we saw some cracks and we were able to document the width of cracks, then we can use a certain reference, for example, this one, which is used to do a post-earthquake inspection to somehow say if the crack is severe or we need to do an immediate intervention. So, for example, if we have a crack scale, we can measure those cracks, and from those determined crack widths, we can determine how how severe, no, the cracks, and how can these cracks affect the overall performance of the building. So in this table, for example, we have a crack width of 0.2, so that's a damage class 1, so probably it's not that worrisome. But if we have cracks of like more than 2 millimeter, then probably we need to do an immediate structural intervention in the building. So that is the importance of the condition specified in the RBS. Now, once this information from RBS are obtained, as I mentioned, it would then allow us to identify what are the necessary tests in order for us to do a detailed assessment. So I would like to use the analogy of a medical doctor, right? When we see a doctor and we feel something in our body, and then we want to see a doctor. And initially the doctor would really ask us what are we feeling, or what's our condition, something like that. And really we just describe what the pain, something like that. And then from those description, you know, the doctor would then recommend some additional tests, like, okay, if you are having headache, something like that, so you may need to do this kind of test, or you may need to do a blood test, something like that. So the analogy is the same in doing this assessment of existing buildings. The RBS is like an interview, okay, that is being conducted by a medical practitioner just to know your condition, the way, I mean, to explain to the doctor your symptoms, the symptoms that you are currently experiencing, and from those symptoms, the doctor may recommend some additional tests. So it's a similar approach. You know, after conducting the rapid visual screening, it should actually help us to identify the necessary tests that we need to perform in order for us to further determine, you know, the causes of these observed defects, or what we call damage, or probably deterioration. So that is now the topic that I would like to talk today about, what are the required tests that we should perform in order for us to do a detailed assessment. Now, the requirements overall for us to do a detailed assessment are as follows. First, we need to obtain copies of what we call as-built drawings. And I understand that for existing structure, in particular heritage structures, availability of as-built drawings is really a problem. And therefore, we can always sort to developing what we call as-found drawings and do some field measurements in order to determine the geometric information of the structural members, and then probably do some non-destructive tools like determining the number of rebars in reinforced concrete, the concrete cover depth, the spacing of the rebars, and so on. Now, after developing this, what we call as-found drawing, then the next step really is to determine the strength of the materials. And for concrete, of course, we need to determine that compressive strength, the yield strength of reinforcing bars, as well as structural steel. Now, we can stop there, okay? We can stop there and utilize the information we obtain from this developed drawings as well as the determined strength of materials. But then again, as I mentioned, if there are some information like observed deterioration, observed defects, observed damage during the RVS screening, then we need to obtain detailed information on these defects. So for example, the cracks. Well, during the RVS, they might mention that there is a crack in this area, but they were not able to note the crack width or the length of cracks or even the depth of cracks. So we might need to do a detailed assessment in those areas to determine the severity of those observed damage. And then we might also want to consider determining the causes of those damage, right? Not just focusing on the symptom, but actually determining the causes of those defects, deterioration, and degradation that were observed during the RVS screening. And these are the requirements, overall requirements really, if we want to do a detailed assessment on existing buildings. Now let's focus on the development of what we call as-found drawing. This roller meter that can also be used to measure distances. And from this information, we can able now to develop what we call as-found drawings. And these as-found drawings will now be the basis of the detailed structural evaluation that we will do. Now, in terms of this, what we call geometric documentation, the needed information, of course, are what we call the orientation, the dimension of the beams, the columns and the walls, the thickness of the slabs, thickness of non-structural walls, because, for example, we also need to account them as loads to the structure. But at the same time, these non-structural walls also provide additional stiffness to our structure. Then it is also important for us to account for what we call story height, okay? And that would, of course, allow us to properly develop a model, right? And then if the building has some roof trusses, then we need to determine the truss configuration and then measure the properties like sizes and thickness of these members, and then sizes of purlins and rafters as well. So basically, we need to document the geometry of the structural member sizes, because in a detailed assessment, our objective really is to model the entire structure and develop a three-dimensional model of the structure. So in order to do that, we need to develop an as-found drawing that would form the basis of our assessment. Similarly, we might also need to do what we call an engineering survey, and the reason for it is really to establish and determine the boundary of the building. Okay, so sometimes it is important for heritage structure as well to pinpoint like the extent of the building. And I mean, it is important both in terms of legal reasons, right? And also important for future development, right? So to establish the boundary of the building. We might also need to do this engineering survey in order to check column alignment and inclination. So it might be difficult to do a visual survey and you can barely notice the inclination of a column, and probably in order to check the alignment of this column, we may need to do what we call alignment survey to determine the inclination of these walls, columns, and the overall building as a whole. And then engineering survey would also allow us to locate the presence of deflection in slabs and beams. So doing an engineering survey is also particularly helpful in determining this information. At the same time, doing such survey would also allow us to document the existing elevation, existing alignment of the building, which of course, based on our experience, is very important, particularly for heritage structure, because we all know that people in the heritage industry are having this really a setback because most of the heritage structure nowadays, there are several developments being conducted near these heritage sites, and this kind of developments can actually damage our existing heritage structure because, of course, our heritage structures are already old and are really vulnerable to this, for example, vibrations during construction, and therefore conducting an engineering survey would give us that information, okay, to document this is the existing condition of the structure before those construction, and if there are any deflection beyond or after the conduct of the engineering survey, then we can say that such deflection is due probably to the neighboring construction, so something like that. So that is why it is also important to do this, what we call engineering survey, to document our existing structure. Now, there is a advanced way of doing it, and that is through what we call non-contact measurement using 3D laser scanners. And the use of this 3D laser scanners allows us to document into detail the entire structure as a whole. And these are just samples of 3D laser scanning, and this one is the laser scan that was conducted for San Sebastian Basilica, a project that we are currently working with the San Sebastian Basilica Conservation and Development Foundation. And through this, we were able to really document into detail, particularly important in this type of complex structures, right? Because really you cannot just go there and measure the details of this one, right? So, and the best way to do it is to do the 3D laser scanning. And again, it allows us to document the building geometry with specific details. And this is important in ensuring that we can do a reconstruction of a certain heritage site. And I think it was also performed for the case of some of the heritage structure in Europe where they were damaged, but because of they were able to keep some digital documentation of the structure, they were able to reconstruct it. So that's the importance of having what we call digital documentation. Now, as I mentioned, for the case of a reinforced concrete structure, we can able to identify we should able to identify the number of reinforcing bars, and in particular determine the concrete cover depth, which of course we need for reinforced concrete design. And we do that using rebar scanning techniques, and those techniques can be either using a GPR, as shown in this slide, or some higher level techniques, which, for example, Hill TPS 250, where it allows us to scan or X-ray the reinforced concrete and really shows you the spacing of reinforcing rebars, and will able also to give you the concrete cover depth as well as approximately the rebar diameter. Now, for structural steel, we can do documentation, right? We can always do documentation of structural steel, like measuring the sizes. But a particular, an important information that we need to obtain, particularly if we have some corrosion issues in structural steel, is the thickness of the metal. And that is because, as we all know, corrosion minimize the thickness of these metals, and therefore, in doing some structural assessment of steel structure, we need to determine the actual thickness. Okay, we need to determine the actual thickness, which clearly it's difficult to do using like a caliper. And we do this with the use of a technique which we call the ultrasonic thickness gauging, or UTG, which allows us to measure the thickness of the metals. And this is really particularly helpful in corroded structural steel. And with this information, we can even model the variation of the thickness of the structure, which allows us to fully analyze the severity of corrosion in the structure, and therefore we can also model the correct thickness of the structure when we try to develop a structural 3D model. Now, for material strength determination, of course, we have the concrete compressive strength is, of course, the most common type of test that we do for concrete in order to determine its compressive strength. Now, as per ACI, this is the only allowed method aside from the pull-out test in determining the compressive strength of concrete. Now, for heritage structure, we understand that this is a semi-destructive technique, and we always want to minimize the amount of core samples that we take from this heritage structures, because we don't want to damage our, we don't want to damage the condition of our existing structure. So we minimize it. We minimize the number of core samples that we take. Now, but in order for us to really get a acceptable level of confidence, we need to get at least 3 samples, right? Because we understand that tests from core samples there are some variability, okay, in the results, and therefore a minimum number of samples is necessary to somehow give us that acceptable level of confidence. Now, in terms of sample size, the sample size in terms of the diameter must be at least 3 times of the aggregate diameter. The reason for this is if the diameter of the core samples is lower than 3 times the aggregate diameter, then the variability of test results increases. Okay, that is the reason why they try to limit the diameter to 3 times aggregate diameter. Then it is also necessary to note that the size of the sample that we use for this compressive strength testing of these core samples is to maintain the height to diameter ratio to greater than 1. And again, this is related to the variability of the test results that was observed in the experiments, that a lower H by D ratio would have a higher variability. At the same time, based on concrete mechanics, of course, samples with lower height to diameter ratio tend to have a higher compressive strength, and that is due to the confinement effect that is provided in between the plattens. And that is the reason why the height to diameter ratio is recommended to be at least greater than 1. But really, based on experience, the preferable H by D ratio is really 2.0. Now, it is also important to note that the sample must be tested within 7 days after extraction, because beyond that, again, there is a high variability in terms of test result. And as much as possible, we need to extract these samples in accordance with a standard, that is ASTM C42 for the case of the Philippines, and then test under compression these samples according to ASTM C39. Then, after obtaining this test results from the cylinder, we don't just take the average of this test results. What we do is we analyze them and consider several factors that somehow influence the compressive strength. And again, there are some correction factors that are dependent on the type of parameters like core diameter, a correction factor for moisture content, a correction factor for height to diameter ratio, as well as a correction factor for curing method. So all this information must be taken into account before using the compressive strength results. So meaning, after doing the compressive strength test, we cannot just take that number and take the average and use it in our assessment, but rather we need to account for these correction factors before we can use those information. Now, another test that we use to somehow relate it to compressive strength is the rebound hammer test. So I did not use the word use it for concrete strength determination because it is not really, I mean, rebound hammer is not really for determining compressive strength, but rather to determine the uniformity in the compressive strength result. As a matter of fact, the codes do not allow you to use this rebound hammer technique in order to quantify the compressive strength of concrete. So the reason is there are several factors that influence this result from rebound hammer tests, and those are the surface condition, test direction, moisture condition, the presence of steel. If you happen to do the test in the exact location of your reinforcing bar, then you will have a higher hardness test, and then the same thing is true for heating an aggregate during the testing. At the same time, carbonation, if there is a carbonation in concrete, it would also affect the result because carbonation somehow increases the surface hardness of concrete, and therefore an increase in carbonation would result in an increase in rebound number, which if you are not aware of that mechanism, then you would think that you get a higher compressive strength component. Actually, that compressive strength is due to the effect of carbonation. So it is very important to note that a rebound hammer test should not be used to quantify the compressive strength of concrete. Now, in terms of structural steel, the method of determining the tensile properties is well defined as described in ASTM 8370. And basically, the important here is to ensure that the sample collected passes the dimension requirements as per ASTM. In terms of the number of samples, well, ASCE 41 really understand that since steel, unlike concrete, is more homogeneous, right? So really, if we have as-built information, then we don't need to test the reinforcing steel and just use the information from the as-built drawings. But if we really want to determine the tensile properties of steel, we need to test at least two strength tests for a given building, as per ASCE 41 standard. Now, we might also encounter some heritage sites wherein the main material is masonry, and in that case, we may want also to determine the strength of that masonry, what we call the compressive strength F prime M, and a semi-destructive way of doing this is what we call a flat jack test. It's a method that was performed in some of the churches in Bohol. It is actually a semi-destructive method that is used to determine the stress-strain relationship of masonry between pre-identified points. Now, what is being done is they would create some incision in the existing masonry and place this flat jack, and using a hydraulic machine, they would apply the force here. But before doing that, they would then mark some points here in this location, mark the the location between 2 points at the initial load zero, and then while increasing the load, they measure the displacement between these 2 points. And by doing so, we can, of course, generate a stress strain curve for masonry and get what we call the elastic modulus. And we all know that for masonry, the elastic modulus is always directly proportional to the compressive strength of the masonry. So from that elastic modulus, we can somehow uh, get some estimate of the strength of the masonry. So this is the detailed procedure of doing it. They try to get a sample area around 200 millimeter in height, then place some monitor displacement in selected areas such as this one, and then pressure is applied in this flat jack using a hydraulic machine manually, and then displacement are measured between 2 points, and again, stress strain curve can be developed uh, based on the measured displacement and applied load. Now, as I mentioned, after determining the after developing the plans, as on drawings and geometric documentation, then we determine the strength of materials. Then we also want to do a detailed assessment in terms of the deterioration and defects that were observed uh, during the RVS. And these are the tests that can be conducted on site based on the observed defects and damage. First is crack mapping. Again, during the RBS, we just took note of the presence of cracks in the structural elements. But if we want to determine if these cracks are severe or needs immediate attention, then we need to do what we call mapping. Now, in doing so, we can relate the crack width in some allowable crack widths that are, for example, given in ACI 224. So, for example, here, these are a table showing you the reasonable crack width in reinforced concrete under service load. So, you can measure those cracks and compare those cracks from this table, and you can judge that, okay, from this crack, I may need to do further assessment because, for example, the crack is more than 41 millimeter, and although it might not be an issue in terms of strength, but it might probably an issue in terms of the durability, right? So by doing this crack mapping, it allows us to determine which among these cracks would need further assessment. Now, in order to do that, so for example, if we have a crack width of greater than 0.41 millimeter, then the next question is how deep is the crack? And the one way to actually measure the depth of the crack is using a ultrasonic pulse velocity test, right? And the UPB, which allows you to measure the crack depth, follows the same procedure described in BS 1881 standard, wherein, according to that standard, the crack depth is a function, okay, it's a function of the measured time travel of the pulse, okay, that was induced on concrete using this what we call transducer, okay, and from those information, okay, we can get the value of C, which is really the measured crack depth, okay, and crack depth is important because it would then allow us to compare the depth of this crack with the concrete cover meter. And it is important because we know, for example, for the case of reinforced concrete, that if the crack depth reaches the reinforcing bar, then that means there's already a potential for corrosion in the reinforcement because there's already a pathway, okay, of contaminants to this reinforcing bar, and that is the reason why we would like to determine the crack depth, right? So if the crack depth reaches a depth that is similar to the concrete cover depth, then there is already a durability issue, and we could expect that corrosion can or might already be happening in our reinforced concrete member. Now we can also use the ultrasonic pulse velocity to allow us to determine the quality of concrete, or if there are any presence of voids or internal cracks in concrete. Because the UPB, as given in this diagram, again, when you use UPB, you actually apply pulse, and that pulse travels into concrete, and the time that it travels, okay, through the concrete depends on the presence of crack, right? Because the velocity, the pulse velocity for concrete is generally constant, okay, regardless of strength. So if the pulse velocity is constant, then we can then use that information to somehow compare it with the actual velocity measured on site, because from that measured velocity, we can then classify if the concrete is or has some internal cracks or voids, something like that. And it also allows us to determine the quality of concrete. Now, this is a table that shows you a relationship between that longitudinal pulse velocity measured in concrete in terms of concrete quality. Like a good concrete will always have around 4,500 value or 4.5 kilometers per hour pulse velocity, but while a very poor concrete would have a lower pulse velocity. So that is also a good way to somehow determine the quality of concrete. Another test that we can do to determine the condition of the structure is what we call a video endoscopy. This is very useful, particularly in difficult to access areas. Right? It allows us to determine the composition and presence of cavities in a structural member wherein access is really difficult. And with that, we can determine presence of defects, internal defects, which of course are difficult to do using a simple visual inspection. Now, how about the tests that we can conduct in order to determine the causes of deterioration and degradation? One is what we call the carbonation test. And I mentioned about carbonation before when we talk about rebound hammer tests, because I mentioned that carbonated concrete would have a higher compressive strength. And this test, the carbonation test, is really performed to determine the depth, what we call the depth of carbonation. And in doing this test, we use a reagent solution, phenolphthalein solution, which when sprayed into concrete, turns concrete to magenta if it is not carbonated, and colorless if it is carbonated. Now, this is an example of carbonation test performed in a reinforced concrete. And here in this photo, you can see here, this is the concrete surface, this is the exterior surface of concrete, and you can see a portion of that concrete that remained colorless after the application of phenolphthalein solution. And that thickness is what we call the carbonation depth, right? Because this is now in what we call carbonated concrete, or the depth of carbonation. Now, the process or the mechanism of carbonation in concrete is really natural because it is a mechanism that involves carbon dioxide, which of course is present in our environment, and that of water. And when these two reacts, they form what we call a carbonic acid. Now, that carbonic acid, when reacted with calcium hydroxide, which is really one of the byproduct of concrete hydration, then results to what we call calcium carbonate. Okay, and this is what makes concrete surface hard, no? And ito yung nababasag ng ating rebound hammer. Okay? And that is the reason why the surface of concrete becomes hard, no? Due to carbonation. And that is the mechanism involved. Now, in terms of the reinforcing bar, what carbonation does to concrete is that it really damages what we call the passive layer in concrete. The passive layer is the layer between concrete and the reinforcing bar. And this layer has really a very high pH. Now, due to carbonation, this pH level is reduced to a level wherein it would already initiate corrosion. So that is why carbonation is really detrimental to reinforced. Really only happen due to possible application of like the icing salt, okay, which of course in the Philippines we don't have, or it can be present as a natural component in an aggregate. Okay, so overall, I would say that the chloride issues in terms of concrete here in the Philippines is not really that much in comparison to carbonation. Now, this is a sample test result of a carbonation test. As you can see here, the percent chloride was presented in terms of percent mass of cement, and then we compare it with the ACI threshold, which is around 0.15 mass of cement. It is also important to note that when you do this test, the lab would also ask you to allow them to determine the cement content, right? Because that's the only way they can able to present your result in terms of mass percent of cement. Okay, so for example, if there is already some signs of corrosion in your reinforced concrete, then probably the next test that you should do is what we call the Hapsel potential. And really, this test is performed to really determine the extent, okay, of corrosion in your reinforced concrete. So if there is already a surface manifestation of corrosion in reinforced concrete, then what we need to do is to determine the extent of this corrosion, okay? And this is achieved by doing what we call a Hapsel potential test. And this is non-destructive. We don't need to expose reinforcing bars. And therefore, it allows us, the test really allows us to delineate the area with corrosion, okay? And this is the actual machine that is used to measure the Hapsel potential. And as you may know, corrosion is an electromechanical process, and there is what we call a transfer of electrons. So really, the Hapsel potential measures those potential difference, okay? Because again, corrosion is an electromechanical process, and there is always this movement of electrons. So those difference in those potential is what the Hapsel potential is measuring. Now, using the actual test, you can then plot the data of the Hapsel potential. This is the Hapsel potential map, which would then show you the area of corrosion concentration. So you can then say that, oh, this area is where the corrosion is happening, and then you can focus your repair in that area. It is also important to develop a cumulative frequency distribution, which will then allows you to determine how much percent of the concrete area is corroded. And for example, here, normally they select like 250 as the boundary. Then this is the area that is corroding, so less than 10%, something like that. So you can then say that how much severe, right, the corrosion activity in the selected concrete area. So that is how we use this Hapsel potential. Now, we can also combine the different tests that we perform by what we call combined methods, and basically it uses a coupled non-destructive test result with semi-destructive test result. And one of the most commonly used method is what we call the SONREB method, which provides an additional reliability in evaluating the concrete properties, using non-destructive procedures and destructive procedures. Generally justifiable only if a reliable correlation for a particular type of concrete is developed. Now, there are several models to consider when we would like to use a combined method, but one of the commonly used method is the one with Schickert, developed in 1984, which is also introduced by Ryland. Here, it expresses the compressive strength of concrete in terms of the measured ultrasonic pulse velocity and the rebound number R. Now, the unknown, are this parameter K sub O, parameter N, and M, which can be determined by conducting or utilizing the data from actual test result, and then empirically you can relate those obtained test results, and you can use to develop these parameters, and from those developed parameters you can then use the equation to estimate the strength of concrete in remaining areas. Okay. So for example, these are the test results for 6 locations, and we have compressive strength results, we have ultrasonic pulse velocity test results, we have rebound number test results. And what we do is we try to collect this model, collect this information, and create a model, okay, or fit the model in this, for example, in a power relation format. So we linearize that one, okay, we linearize that one, and then from there we determine the parameters involved by using the least square method. And from this analysis, we can develop an equation which we call the Sonrev equation, which then we will use to quantify the compressive strength of concrete without the need to conduct more semi-destructive tests, without the need to take more concrete samples. So that is the purpose of developing a Sonrev equation. So we can limit the number of core test samples to 3, for example, and then we can just increase the number of samples for pulse velocity and rebound hammer, and then for the remaining area to confirm the compressive strength, we just use this equation and use non-destructive tests for the rest of the structure. So that is one way really to reduce the amount of semi-destructive tests and also increase the reliability of our non-destructive test results. Okay, so now I would like to talk about the benchmarking techniques. And why do we need benchmarking techniques? Well, we need to benchmark the test data because we need to ensure that the collected information from the test matches the existing performance of the structure and the structural elements. And we also needed to verify the appropriateness of the assumed loads and also to validate the performance based on actual condition. Because, for example, if we use collected dimension of a column and the number of rebars obtained from rebar scanning, then the strength of concrete plus the strength of the concrete that was obtained from the test. And what we do is we calculate the capacity of the column, right? We calculate the capacity of the column from the obtained number of reinforcing bars, from the obtained compressive strength. And then when we try to check the capacity and compare it with the actual demand, okay, then the column failed the gravity assessment, right? Which is not consistent because the existing structure is standing and is currently being utilized, right? So that is the purpose of benchmarking. We need to check if the test data, okay, and the actual capacity of the structure matches the condition of the structure. So one possible reason for it is that again, the rebar scanning technique, although it is already advanced, I mean, it has still some limitation because, you know, the estimate of the diameter is not really that accurate, that we might underestimate the diameter of rebar, right? And in doing so, by underestimating the diameter of rebar, we are also underestimating the capacity of concrete. So if the capacity of concrete doesn't match the demand, then it's either that we are underestimating the number or diameter of rebars, and also we might also overestimating the amount of gravity loads that we use in our assessment. Okay, so tatanungin natin, we use this information. For example, we have 820 mm diameter. We took the capacity and we compare it with the demand, bagsak siya, no? So, which is not consistent because nakatayo yung existing structure. So that's the purpose of benchmarking. We need to check if the information we obtain matches the actual condition. So in doing so, we need to check if we are using the right gravity loads in our assessment, or if the number of reinforcement or diameter of reinforcement we use in calculating the capacity are actually accurate. We can also assess the performance of our building in terms of historical earthquakes, right? So the question is, how come this existing structure survived, right? Several earthquakes, no? And we are talking about structures more than 50 years, no? And clearly in those 50 years, this structure was subjected to a certain level of ground motion. And to do that, we can make use of some tools like the shake map, which allows us to collect information about the past earthquakes that have occurred near our area of interest. So, for example, in Metro Manila, if you will collect the records of earthquake with magnitude 5 and greater, okay, so you will see this earthquake locations, right? These are all actual locations of earthquake epicenters within Metro Manila. And from here, you can then estimate how much the earthquake intensity that was experienced by my structure when this earthquake occurred, right? And so, for example, here, if I have a structure in Manila, it seems that this earthquake in April 2019, which is a magnitude of 6.1, I was able to calculate an intensity at the site location of 0.10 G, which is, of course, less than code design earthquake. Now, I will then use this 0.10 G earthquake to assess the performance of my structure. Okay, I will then perform seismic analysis using this reduced level of PGA. Okay, it allows us to also assess if, for example, if our structure really did not have a damage during this earthquake, then in my analysis, all my members failed under this 0.10 G, then there's something wrong in the way I modeled my structural building, right? So that means my model doesn't match the performance of my building during this earthquake. So what are the steps in using shake map? So this is the shake map tutorial. So you go to the shake map website, USGS shake map website, and then you select the region where you want to determine the historical earthquakes that have occurred in that region. And then step 2, you then filter the magnitude of earthquake that you want to know, and as well as the year, let's say 1800 to 2021, although in the Philippines, really, the record of earthquake, I think, it started around 1920, so it's difficult to get earthquake records below 1920. And then from there, you click the search button, and this is what it will show you. These are all the earthquakes that have occurred in the Iloilo, Visayas region. And then from here, you can then select a specific earthquake of interest. So for example, here, the largest earthquake that somehow Iloilo experienced is the Panay earthquake, which has a magnitude of 7.8, occurred in 1948. Okay, so you may want to determine how much intensity of ground intensity my building experienced during this earthquake in 1948. So you then click that earthquake event, and it will show you this one, which would then allows you to select the information that you want to get. So for example, I want to know the PGA contours based on that earthquake event, and then it will show you this PGA contour. So for example, here in the Iloilo area, in 1948, due to the 7.8 magnitude earthquake, the Iloilo CBD experienced the buildings in the Iloilo CBD experienced an earthquake having a magnitude of around, having an intensity of around 0.2 G. So I will then use that 0.2 G to create my response spectra. So that 0.2 G is somehow can be related to a zone factor 0.2 in our code. So I will then use this earthquake or seismic parameters to develop my seismic response spectra, or to compute for my base shear corresponding to that earthquake event. And that is how we perform the benchmarking using historical earthquakes. I will then use that one and then compare if my buildings would fail under this earthquake scenario. Because if they would fail, then that is not acceptable. Because, for example, the buildings in the Iloilo CBD remain standing up to today. So therefore, I should expect that if I use this information in my seismic analysis, at least my buildings must pass, right? And must not collapse under this level of earthquake. Okay, so that's the importance of benchmarking tools. I would just like to, now, after this one, we can go. So after doing the benchmarking, you may want to proceed in a more detailed assessment, and that is to use commonly, like for example, the ASE 41 to do a detailed assessment, and that would cover what we call a tier 2 and tier 3 analysis. And in doing those tier 2 and tier 3 analysis, you will do the process as shown here. You establish the performance objective, which is related to the level of seismic hazard and the level of target performance, that is how much damage you expect your structure to have for a given level of earthquake. That is really the performance objective. And then you evaluate your building based on that selected performance, and you assess it if that performance is met. And if not, you can revise the design or do some retrofit. Whereas if your building passes the assessment, then the procedure or the evaluation is complete, and therefore you were able to meet that performance objective. The flowchart looks simple, but really there are some details involved inside this methodology. For example, in tier 3, we need to do nonlinear analysis, and there are several things that you should do before you can able to complete a type of analysis. So this really just shows you the overview of doing a detailed assessment, in particular in doing tier 2 and tier 3 analysis after you obtain the RVS result and after doing the semi-destructive and non-destructive test that was presented to you today. So that would be it. And thank you for your kind attention. Thank you for listening.